You're most welcome for this lesson. And today we are going to be looking at derivatives of exponential functions. So when we talk about exponential functions, it is written as e, and then here we can put the x, or it depends on the variable we are dealing with. And the graph of an exponential function is an increasing curve that goes in this format. So like when you look at this graph, this is how an exponential graph looks like. And what is the rule for exponential functions? Whenever you have an exponential functions, the general rule is that dx of an exponential function with respect to x always is given as ex. So whenever you differentiate an exponential function with respect to x, you remain with the same thing. You remain with x e power x. So an exponential function, once you differentiate it, you remain with the same thing as long as our power here is just x and there's nothing else that accompanies it. But how does the general rule look like? Now, our general rule, we are going to derive how we reach to that conclusion. So we are going to say that let our y equals to e f of x, that we have written our exponential functions and our function will be in terms of x. Now we are going to use the chain rule. We know well that from the chain rule, when I have the y, the x is the same as having the y, du, then times our du dx. And this is what we call the chain rule. Now, depending on the function we have y is equal to e f of x. So I'm going to say that let my u equals to f of x. Now, what is going to happen? Since I want here in my function here in my chain rule, I'm looking for du dx. I'm going to come and I say my du dx will be the same as f prime of x. But still, you know very that now since we have let f of x is equal to u, it means that our y will be e power u, meaning that our dy du is going to be eu, because we have already said that whenever you differentiate an exponential function, you remain with the same thing. Now the answers we have obtained, now we are going to go and feed them back into our chain rule. So this answer we have here, we are going to bring it and feed it here. Then this answer we have here, we are going to come and then feed it in that position. So what are we going to have? Now we are going to come back and say our dy dx is equal to the dy du, which we obtained as eu, then multiply times du dx, and our du dx is f prime of x. Now, when we substitute back our e power u, it means that our dy dx will equal to e f of x, f prime of x. And now this one, I can rearrange it very well, and I write it as f prime of x, e f of x. And now this is what we call the derivative of the exponential function. And now this one is going to be very important whenever we are differentiating any exponential function. The first thing you have to do, always look at the function. You are not saying that in order for you to differentiate it, always you get the function, which is f of x, differentiate it. So you place it at first, and then after you write the original thing. And this is the general rule we are going to be applying. If you go back at what we had, you notice that here we had e to power x, meaning that our function of f of x was just x. So f prime of x is equal to 1. And therefore, it means that when you substitute here you have 1, then write the original function, which is e of x. So this one is the same as e of x. So now that is our general rule, and that is what we call the derivative of an exponential function. Yeah, let me hope we are on the same page. Now we can dive deep and start working on some examples concerning exponential functions. And our first example is going to be e power 3x. Now, it is always a good practice to first let. So I can say, let my y is equal to e 3x. Now, like you have noticed that our exponential derivatives come from the chain rule. So if we want to do from the first principles, then we shall say that let our power, here our power of the exponential is 3 power x. So I will say that let u equals to 3x. And then I will have now my y is equal to e to power u. Then since we have used variables, a variable of u, then we are going to use our chain rule. And we know that our chain rule always tells us that my dy dx is going to be dy du, then times the du dx. Now your task is to differentiate dy du and also you obtain du dx. So I have my u already as 3x. So to get my du dx, I'll say du dx. And we know that from differentiation, we know that our rule in differentiation that x to power n, you always drop the power, which is n, then reduce the power by 1. That is our rule whenever we have we are getting whenever we are differentiating with respect to x. We are going to apply the same thing. Here, our power is a 1. So when it drops, it means we shall have 3 times 1, then x, then you reduce the power by 1. So this will give us 3x to power 0, and any number to power 0 is equal to 1. So do not forget that x power 0 is the same as 1. So here we have 3 times 1, which will end up with 3, meaning that our du dx is the same as 3. Then when I go back, I'm going to look at my second one, which was y, and our y is equal to e power u. So to get dy of our function, which is eu, it is the same thing like that, e to power u. Therefore, now I'm going to go and substitute. So this is du, dy du. Then I'm going to go back and I do the substitution. So when I'm substituting, I'm going to, where there is d du, I'll put e power u. Where there is du dx, I'll put 3. So I come back here in my chain rule and I can say that my dy dx will equal to dy du, then times the du dx. So I've obtained my dy du as e power u, then times my du dx, which is 3. Then I'm going to substitute back, but I'm going to arrange, I start with the digit, then I bring back the function. So I write eu, but I know that u, we obtained it as 3x. So I'll say now 3e 3x. And now this is my dy dx. So that is how we differentiate our function. Let me hope we are understood that. Okay, we can try out the second number. Our second number, we have e power negative 5x. So still we shall first we shall say that let y equals to e negative 5x. Then we are going to let our function. So we shall say, let our u equals to e negative 5x. We always let out this power here, such that always we have just one variable up there. So now here we shall know that our du dx is given as negative 5. Because like we have noticed that when I differentiate here, there is a power 1. I drop the power, I subtract 1, and any number to power 0 is that same thing. Then I'll have now my y equaling to eu. And when I differentiate this with respect to I will get dy du is equal to eu. Therefore, I'm going to come back in my chain rule and then I substitute. So we shall say dy du is equal to dy dx is equal to dy du, then times du dx. So my dy du is eu, then times my du dx, which is -5. So here I'll have e, but our u was initially -5x. I'll replace it with -5x, then I multiply times -5. And I can write it as -5 e -5x, and this is my dy dx. So that is how we differentiate it. But also remember from our rule, from our general, we have said that whenever we have the x of any exponential function, let me say e f of x, we have said that this is the same as you having the derivative, then after you write the original function. So if I apply this, here our function f of x is equal to -5x. So meaning that your f prime of x will equal to -5. Do not forget that f prime means you are differentiating one time. So now when I go back here, I can come and I say that now my ddx of e power -5x will equal to our derivative, which is -5. Write back your original function. So this is the second approach you can do, or using that simple approach. So that is how we differentiate. Okay. Let me hope we are on the same page. Okay, we can try out another one. Number 3, we have e x power 3 minus 5. Still here we do the same. Let y equals to e x power 3 minus 5. So we shall say that let our u equals to x cubed minus 5. So we are going to differentiate. So I'll say that my du dx will equal to, I drop the power, so I'll set 3x, then the power here I reduce by 1, minus, remember this one is is having like x to power 0. So the moment you drop, it means you have 5 times 0, x power 0 minus 1. But anything multiplied by 0 is 0. So meaning that here we have our du dx equaling to 3x squared. Because this one, everything is going to vanish because you have you are multiplying times 0. Then our y is equal to e, but since you have already let that your u is x3 minus 5, then it means that I'm going to just put here power u. Then I will say the y du will equal to eu. Then I go back to my chain rule and I say that the y dx is equal to the y du, then times our du dx. So the y du is equal to e power u. I multiply times du dx, which is 3x squared. So here I'll end up with my e to power u, but u was x cubed minus 5. So I'll say e x cubed minus 5, then times 3x squared. Therefore, I can start with 3x squared. I say 3x squared e x cubed minus 5. And that is our answer for our dy dx. Alternatively, you can use the other approach and say that I know very well that whenever I have dx of e of f of x, this one is the same as having f prime of x, and then I have my original function back. So now for this case, we shall say that d dx of our e, this is x cubed minus 5. So our function here, our f of x is the power, which is x cubed minus 5. So when you get f prime of x, you end up with 3x squared. So here we shall have 3x squared, then write back our original function, x cubed minus 5. So that is the second way you can approach. The first way is when you are getting the derivative from the first principles. But after you mastering this first principle, you are going to come to see that you always just have to differentiate what you have the power, and then after write the original thing. Okay, I hope we are good to go. We can try out another one. We have another one. Y is equal to EX squared out of X. Now, as we approach these exponential functions, sometimes we may need to bring in other laws. So when you look at what we have here, it shows us that now we need to bring in what we call the quotient rule, because we know that whenever we are dividing in differentiation, we bring in what we call the quotient rule. And how does the quotient rule state like? We know very well that we say that our dx of our function u out of v, whereby u is the numerator. For this case, this is the numerator and this is the denominator. So you need to first identify what is your numerator and what is your denominator. So this one will give us v du dx minus u dv dx, everything out of our v squared. Now, we are going to identify what is our u, what is our v. So your u is the numerator, your v is the denominator. In other words, the number that is up is the u. The number that is down is the v. So now I'm going to say that my u is equal to EX squared. Now I'm going to obtain my du dx. So like we have said here, we shall have du dx. Now, we just have to differentiate the power. We shall get 2x, then we write the original thing. Whereas our v is equal to x. So here we shall say our dv dx is equal to 1. Why? Because you know that this is x is to power 1. So I'll drop the 1, I'll get 1. Then I write x, then I say 1 minus 1, which will give me 1. X power 0 and x power 0 will be still 1. Then after doing so, I'm going to come and I substitute in my quotient rule. So I'll say d dx of my u, which is EX squared, out of x will equal to my v, we had as x, times our du dx, which we had as 2x EX squared, minus our u, which was EX squared, then times dv dx, which was 1, everything divided by v, everything squared. Now here you are noticing that when we reach here, you can easily see that this is x and x. So you can multiply them. X times 2x, you get 2x squared. And then EX squared times x, when you multiply these two, you end up with still EX squared. Then this one, you end up with x squared. So now we are going to go to the next step and then we continue. So meaning that our dx of EX squared out of x is going to equal to 2x squared EX squared minus EX squared, everything out of x squared. Now here, we have almost reached our final answer. But since when you look at it very well, you can easily tell that this one and this one are common factors. So meaning that you can simplify it by factoring them out. So when I factor out, it means that I'll have EX squared since it is common. So when I remove it, here I remain with the 2x squared minus a 1, everything divided by x squared. And this is what we call our answer. So you can end at this point because you may not be able to go any further. So that is our answer. But in case you want to go any further, then it is really very okay. But this one is just good enough. Yes, let me hope you have understood how we have come up to that point. Okay, we are going to try out another one. That is number 5. And our fifth one is going to be 2 root of x e to power x. Now, what do you need to know? Whenever you are dealing with differentiation, having the rules at your fingertips will always help you a lot. Now, when you look at what we have, you can easily tell that for this particular one, you are going to need now what we call a product rule, because here we have two functions we are multiplying. We have this as our function and we have this as our function. So that means we are going to say that let one of our function be u and let the other function be bv. So we are going to have our two functions. And you remember very well that our product rule, how does the product rule state like? So our product rule states that whenever I have dx of two functions u and v, this is the same as having u dv dx plus having v du dx. So this is the rule we are going to apply. So I'm going to come and now I say, since I have already decided that my u is going to be 2 root of x, and then my v is going to be e to power x. So when you go back to our rule, you are noticing that in our rule, you don't need what you call here. You notice that you need du dx, but also here you will need dv dx. What does it mean? It means that you need to differentiate. But when you look at 2 root of x, in order for us to be able to differentiate it well, then it means that it is always better we write what we have as our root in a simplified format. So this is the same as 2x power a half. So do not forget that always a root is 2 power half. But in case it is, let me say 3, something like this, then this one is means x power a third. In case you find maybe it is 3, then you have an x squared 2. So here you'll approach it as x 2 power out of 3, like that. So you need to first learn how your root is being written. But do not always confuse them, because at times they can write this. So this one is not a power. Always this 3 here, the 3 is always placed somewhere there, is always placed somewhere there. Okay. Hope that is very okay. So now we are going to continue. So we know that when we are differentiating here, we shall say that our du dx is equal to, we are going to drop our power, which is a half, so I'll have 2 times a half x, then I say a half minus 1. So you can notice that what is going to happen is that these 2 and these 2 are going to reduce. And once they reduce, here we shall remain with just a 1. 1 times 1 becomes a 1. Then this is a half minus 1. So a half minus 1 will give us negative a half. And therefore here, our du dx will equal to x power negative a half. Then when I come back here to my v is equal to e exponential x, here we have already learned that whenever we differentiate an exponential, we shall always get that same thing as long as we only have x. Therefore, after that, I'm going to come and I substitute back in our formula. So when I come back to substitute, I'll have my u here. Here my u, we chose was 2 root of x. Then what is our dv dx? dv dx, we have got exponential ex plus my v, which was exponential x, then times u, which du dx, which is x power negative a half. So when you look at it very well, you can notice that e exponential x are common on each side. So you're noticing that this one and this one are common, meaning that you can be able to factor it out. So I'll have e power x, and here I remain with the 2 root of x, then plus x power negative a half. But you remember very well from our indices that whenever I have a to power negative b is the same thing as having 1 out of a power b. So meaning here I can write e power x into 2 root of x plus 1 out of x power a half. But still, you remember that whenever you have, still from your indices, whenever you have x power a half, this is the same as having root of x. So here I'll have e to power x into 2 root of x plus 1 out of root of x. Now this one, you can easily simplify it further if you want. Because this will be e to power x, then everything can be out of root of x. So if I take my LCM as root of x here, you know there is a 1. So what will happen? 1 times root of x, I'll get root of x. Now when I get root x times root x, let me do some side work here or no. Let me do. When you have root of x times root of x, here, you know, this is x to power half times x to power a half. Numbers of the same, when numbers are to the same base, you add the power. So I can say x a half plus a half, which will give us x power 1, which is the same as x. So here, I'm going to remain with, here, I'll remain with 2x, then plus root x divided by root x is 1, then times 1. So then that is going to be now my answer. So when I'm writing my final answer, I will just say that my final answer is going to be ex into 2x plus 1, then everything out of root of x. So that is what we get when we differentiate. Okay, let me hope we have understood up to that point. So that is how you differentiate exponential functions. So you have noticed that you can apply very many rules. You might find that this time around you need a product rule. The other time you need a chain rule. The other time you need a quotient rule. So you need to be well conversant with all the rules in order for you to be able to do such numbers. Okay, let me hope we have understood very well on what to do when it comes to the differentiating of exponential functions. In case you have any question, feel free to ask. Okay, we can do one more, I think. We can do one more. We can do one more. Okay, one more. Okay. Okay. We can be given something. We can be given, take an example. They have given you, you have such a function, x, and then still you find that your power is ex. Still, even if your function is like that, you have to differentiate it. So what do you need to do? One, you have to let. We can say that let my function y equals to ex. Now, afterwards, you are going to let the whole of your power here equals to u. So you say that my u equals to ex. Now, what do you notice? That here now you have ex, meaning that you need now to apply our product rule. So I'm going to come back here and now allow me to use red. So when you look at this one can be, I don't want us to confuse them. You are going to allow me, since I'm using, you are going to allow me here. Still, you need to know the product tool. So do not cram UV. So you are going to allow me here to use U, still here to use my V, such that we relate very well to the product tool. So we know that our product tool will states that the x of UV is always equal to U, the V, the x plus V, the U, the X. So if you want, you can always have this U. You may not call it U to not to confuse it, so you can change it and you say, maybe let me call it W. It is very fine. So here our U is X. So I know my U is equal to X, meaning that my du, dx, will equal to a 1. Then my V here is equal to e power x, meaning that my dv dx will equal to ex. So now you can substitute. So our u is x. I will say x. My dv dx is equal to e power x plus my v, which is ax, then times du dx, which is times 1. So here I will end up with ex, then plus e power x. So this is my my dw, what I have as my w. So here I can end up saying that since ex is common, I'll have ex into x plus 1. Now, after finding that, remember we had our y equaling to e, now w. So in order for us to find it, we shall say that the w is going to give us e w. So we go back to our chain rule now. Now, what does our chain rule tells us? It tells us that whenever I have the y, the x, this one can be the same as the y. Now, since I've used the w, I'll say the y, the w, then times our dw dx. Now, our uv here, what we differentiated was the dw dx. So this was our dw dx. So I'll come here and I say my dy dw is equal to ew, then times the w dx, which is ex into x plus 1. So since I know my w already is ex, here I'll have now to say uh, ex, then times my ex into x plus 1. Now, what do you notice? Now, one thing we are going to notice is we are going to ask ourselves, can we collect like terms? Yes. So allow me to first take x plus 1 out. So I can say x plus 1. So when I take x plus 1 out, I remain with ex. Then I have another ex. Then I have ex. Hope that we are still on the same page. Now, when you look here, you are noticing that this e and this e, they are the same. And you know from indices, whenever I am multiplying AB times 8 power c numbers of the same bases, I can always reduce, I can always add the power. So this means AB plus c. Now, for our case here, what are you noticing? You are noticing that we have ex, then times ex. So our power here is going to be ex plus x. So now I'm going to come and I say this is x plus 1. Then I'll have e into ex plus my x. So you notice that x is common. So meaning that I'll have x plus 1 into e, then I factorize out x, then here you'll have 1 plus e power x. Hope that one is still very okay. Because x is common, so I can factor it, and I remain with something like that. Hope that is very, very okay. So now, if I want, I can have my answer up to that point and I stop there. So that one is really very, very okay. So you may end at that point. Okay, let me hope you have got how we can deal with such numbers. Okay, so allow me now that at least you try out an exercise. You try out an exercise on your own. Yeah, so our exercise that we are going to do, this is the exercise that you are going to try out. Oh, the exercise that you are going to try out. So this is your exercise. Kindly try it out. Try it out. Those are the numbers that you're going to be dealing with. But maybe to throw more light, take an example. When you are dealing now with such a number where you have 5 root of ex. So here, you know that This one is more or less like a square root. So you can write it in terms of a half. Yes, you can write it in terms of a half. So mean that that is the same as 5 ex everything to power a half, which is the same as 5e exponential x out of 2. So that is the meaning. So you differentiate it in that format, but still you follow the same procedures. First come differentiate what you have as your power. After differentiating what you have as your power, you'll have f, that will be your f of prime of x. Then after, write the original function. Other numbers you are going to try out are here. Yes, that are going to involve you to learn how to use the product rule and then the quotient rule. Okay, so we are going to end here for now. We shall continue from here when we meet again. Thank you so much for attending and have a lovely day.